we'll take a look at some three-phase review. You might recall from third year that each phase winding of a three-phase machine is 120 electrical degrees apart from each other. And these phases are labeled A, B, and C, and color-coded according to the Canadian Electrical Code. It can be connected either Y or delta. And we have some rules for Y, which is also known as star. E line equals E phase times root 3. And I line equals I phase. We can safely say that voltage adds at 60 degrees. When we look at A vector and B vector in their normal phase rotation, and then we place B vector at the head of A vector, we have to draw it in the opposite direction. We have 60 degrees from the horizontal. So if we take our phase voltage and times it by the square root of 3, we'll have our line-to-line voltage, which is the same as saying 120 volts at 0 degrees plus 120 volts at 60 will also give us the line-to-line voltage, in this case of 208. Current adds at 120. If we have a fully balanced Y-connected circuit, we took our A vector and placed it head to tail with our B vector at 240, I should say, and then our C vector at 120. We would have 0 current in our neutral. If the system was unbalanced, and we did the same vector diagram, we can see here that they are not the same size, so we have the vector sum of current in our neutral. In a system or a Y-connected system, if we have an open fuse or an open phase winding, it will produce 50% power. It's also known as single phasing. And if we happen to have a neutral in this system, and we have the same scenario, open fuse or open winding, our total power produced will be 66.67%. I will look at these calculations in a little more detail in another presentation. For delta connection, for the rules, this is also known as a mesh connection. E line equals E phase, and I line equals I phase times the square root of 3. For the delta connection, we could say voltage adds at 120, and when we place our voltage vectors, in this case, head to tail, you can see that we are right back to 0, which is where we should be, and we could do a mesh test, or what we call a delta closure test, to measure for 0 volts across those 2 points. If we get something other than 0, then we shouldn't make the final connection. But that value would be quite large compared to some ghost voltage. Here's what would happen if we had one of the phases backwards. If each of these were rated for 120 volts, from the tail of B vector to the tail of C vector, we would read 240. So not a good time to close. For current, as with Y, for voltage, it adds at 60 degrees. And once again, if we take our phase current vector and place them head to tail, like we did here with our voltage vector for Y, and we had 10 amps in each of the phase, and we multiplied by the square root of 3 to get our line-to-line current, which is the same as saying 10 amps at 0 plus 10 amps at 60, which is our angle here from 0. In a delta system, if there's an open fuse, this is also known as single phasing, the circuit would only produce 50% power. If there was an open phase winding, the power produced would be 66% power. And once again, we'll look at those calculations in a little more detail. For both Y and delta connections, VA, voltamps, or apparent power, equals E line times I line times the square root of 3. which is calculating for the volt amp or the hypotenuse of our power triangle. Power in watts is E line times I line times the square root of 3 times our power factor, which is our cos of the angle. Of course, we're calculating for the base of the triangle. Also, we could use VA equals E phase times I phase times the square root of 3, as well as power, E phase equals I phase times 3. I think I said square root of 3 up there, but it's times 3 times the power factor will give you watts as well. For VARs, if we have a capacitor bank, we have the line voltage and the line current of the capacitor bank, we could figure out the VARs of that bank following the same method. Now the four fundamental connections to the three-phase transformers are YY, delta delta, delta Y, and Y delta. And we'll look at those in a little more detail later on as well. Bye for now.